Lucky, good evening. Namaste, Harsh. Gopal, good evening. Let's start the class. Yes, prepare well. Okay. So, this is your chapter, logic families and semiconductor memories. Let's start this. Okay. So, in this, what we are going to discuss? What is logic family? Logic परिवार. Family का मतलब क्या परिवार? So, logic परिवार का meaning क्या? So, till now in our digital we have done like this only. Whatever may be, we have never one time we have checked, but we have not worried about what inside this, what is present inside this, which is important as a VL. Suppose you, because you are EC people, your favorite branch, if you want as a VLSA engineer, so you must know much about it, much more than this class also. This class, yes, with respect to grade, whatever required, that point I will cover. So, how to make the gate? There are different ways to make the AND gate, different ways to make the OR gate, different ways to make the different gates. So how to make a gate? That is what we call logic family. Different logic families have different methods to implement it. Let's have a look of different logic families we have from long back. So first thing, earlier days you have RTL, resistor transistor logic. What is the meaning of RTL? Resistor transistor logic. The next one we have is direct coupled transistor logic, integrated injection logic. Then you got diode transistor logic, high threshold logic family, transistor logic family. In that we have different output configurations: open collector, totem pole, tri-state. Okay, in this three: open collector, totem pole, and tri-state output configuration. Okay, lag is there. Ganesh, remaining please comment. No Ganesh. Okay, I am happy. One minute, let me check it. I don't think lag will come. Connection is stable, so let's continue. Ready? So TTL and emitter coupled fastest logic family are there. So in this, okay, they have removed this from gate syllabus. They are not in gate from where 2016. From 2016 they have removed this whole part. Any instrumentation guys are there? Instrumentation? Some people, if they are, yes, Shubham, you are instrumentation guy. Okay, I have small doubt about some kind of TTL part might be present in your instrumentation. I will cross check it once. Okay, don't worry about that. let's continue. So this part is removed from the gate for EC people. Okay, it is not in means in only. It is not IN. Okay, it is not in gate from 2016. Let's don't write capital. It will give more confusion. Okay, but in yes, if you prepare for EST, it is required. If you want, I can provide the notes for that for time being. So now the next part we are going to discuss is this is a transistor based. Okay, now we are coming to MOS logic family. So the present trend mostly your NMOS, PMOS, and CMOS. This is important. Every year for EC people, some one question coming from the CMOS. CMOS is specified in your syllabus. NMOS, PMOS not specified, but CMOS contains NMOS, PMOS only. So we need to discuss NMOS, PMOS only. Then only you can understand CMOS. So this is your gate syllabus. This is in the gate. MOS logic family is there for you. So we are going to discuss that. So these are the different technologies to make your gate. So how to choose which one is best for me? Out of them, I want to select a particular logic family gate only because I love that particular logic family. How to choose that? Any device can be selected based on what? Tell me here. Please comment. Very good. Bhargavi, right. Specifications. Specifications need not be speed only, all specifications. So for the given logic family, like for DAC, ADC, resolution, etc., we discussed now. Like that, here also specifications are important. What are the specifications? The first one we will get is propagation delay. Propagation delay, we call it as TPD. Yeah. So these are the important specifications of any. Okay, now we should understand the meaning of every particular specification. So let's start. Let's start. Let me get that slide. Let me upload the slide. One minute, please. Let me switch off that fan, which is giving more noise for us. Okay. So please read, please go through that. Please go through that and read it. What is propagation delay? It is the time required to get a valid output after applying the input. It is what we call propagation delay of the gate. It is expressed in milliseconds. It should be as minimum as possible. It should be as minimum as possible. Delay should be as low as possible. On what specifications delay is depending? It is depending on storage time of transistor and RC time constant. Let me explain you. Suppose you have a gate. Let's take one example of inverter. Okay, so this is your input, this is your output. In the basics already I discussed this figure, that's why I'm not going through it now. So this is the transistor. When the input is 1, your output will be 0, because it will act like a short circuit. On means here what? Saturation. Similarly, when input is 0, it is off, or you can say it will work like a cutoff. So generally here, the transistor works like a switch. When it is on, it is in saturation. When it is off, it is in cutoff, not in the active in general. So generally, when you change the input, the transistor which is present in your gate may need to change from saturation to cutoff or cutoff to saturation. So the gate need to change from saturation to cutoff or cutoff to saturation. To do that, what we need? It requires little time. That the transistor storage time, based on that, it requires some time to change from saturation to cutoff or cutoff to saturation. Similarly, the load will have, or input will have, some capacitance and resistance. So the load will be having some capacitance and resistance. This charge or discharge will require some time. That is why you need to charge and discharge, sir. So you want to make it 1, you need to charge it. You want to make it 0, you need to discharge it. So all this process requires some time. It may be in nanoseconds or milliseconds, doesn't matter. But it requires some time. Okay. So here, generally, general specification of propagation is depending on, expressed in nanoseconds. It depends on storage time of the transistor and RC time constant. So it should be as low as possible. Let me give you one example. For example, your input is like this. It changed from 0 to 1, and again like this. It changed from 1 to 0. So this is your input. You have applied this kind of input to which gate? Inverter, for example. Then it should change from 1 to 0. When it changes from 0 to 1, it should change from 1 to 0. When it changes from 1 to 0, it should change from 0 to 1. Your input is changing from 0 to 1, output will change from where to where? 1 to 0. Similarly, when input changes from 1 to 0, because it is inverter example I am taking, it changes from 1 to 0, it will change from 0 to 1. This is your output. So now you take this midpoint and this midpoint. Between them, some difference is there now. This is what we call propagation delay when output is changing from high to low. It is the propagation delay when output is changing from high to low. Similarly, when it is changing, input is changing from 1 to 0, output changes from 0 to 1. Here also some delay will be there between your input and output transition. This is what we call propagation delay. This is what we call propagation delay when output is changing low to high. Okay, when output is changing low to high. Here we take the middle point as your reference. When it is changing from 0 to 1, this raise time is also taken into consideration. Okay, so this midpoints difference is TPHL, these midpoints difference is TPLH. Okay, so what is TPD? TPHL plus TPLH by 2 is the general specification to give the propagation delay of any gate. So now please listen. Now listen here. In general, in the transistor, suppose output is changing from high to low. That is, output is generally output is high means transistor is in off condition. You assume inverter. When output is 1, this should be off. When output is 0, this should be on. So output should change from 1 to 0 means your transistor should change from off to on. Here transistor changes from on to off. So generally, in general, propagation delay of low to high requires more time compared to high to low. Why? Because it requires more time for the transistor to change from saturation to cutoff instead of cutoff to saturation. So it requires more time to change from where to where, low to high compared to high to low in general in any gate. Okay, but we take the average as your propagation delay specification. Any doubt in this? Please ask. As a reference, because it need not be same. Okay, you should not take from this to this. Okay, you should here you should judge what we call it is 0, it is 1. You cannot take this one. I mean, actually another way is to do like this. Where is that? 1 to 0, 0 to 1, 1 to 0. We generally show like this only. In this process, what you are neglecting is you are neglecting this time required to raise from 0 to 1 because it is in nanoseconds. That is also important. So if you take from here to here, it may not measure perfectly. So we should consider one middle point as your reference, middle point to middle point. Okay, let's move. Let's move. Now, sir, while explaining setup, hold, TPD, we should that same. There also we take middle only. For all delays, we use the same notation. Okay. Now, for example, let me give you one practical example. In TTL logic family, transistor logic family, propagation delay high to low is 7 nanoseconds. Propagation delay low to high is 11 nanoseconds. What is the propagation delay on an average? Is 11 plus 7 by 2, 18 by 2, 9 nanosecond. This is the important specification. You need not remember because they have not kept this detail right now in your syllabus. So generally, this is the how you measure your TP. So let's see the next important specification. 1 minute. Right. So the next specification is power dissipation. So this is the TPD. Then the next one is power dissipation. It is the average power dissipated by one gate. It is expressed in milliwatts. It is also should be as minimum as possible. Definitely, you need low power devices, high speed devices. Definitely, you require low power consumption. Your battery should not drain immediately, and you need high. What is that? High speed devices. Both should be as minimum as possible. But in general, there is a trade off between them. Suppose see here, you have this kind of circuit. Okay, we have some ways to overcome it. For example, I am showing you. This is the resistance. Okay. Generally, this is the capacitance, for example. Okay, this is your charging time constant tau equal to RC. Now, if R is decreased, R decreases, then what happens? Tau decreases, speed improves. Speed improves. But the problem is when R decreases, current increases and power dissipation will increase. So because of this trade-off between them, we maintain some according to your requirement. Some are high power, some are high speed, some are low power. There are some ways where you can improve both of them, but this is the general what we call trade-off between your power dissipation and the propagation delay. There are ways to overcome this. So we calculate power dissipation as in general direct formula is VCC into IC average. What is IC average? For transistor I am saying IC is equal to IC average is collector current when the output is high plus output is low. This is not required for you, but I am saying when output is open circuited and output is short circuited, different cases you get a different currency, not same. So we should take average every time. Next, figure of merit. Please listen. As the name is indicating merit, it need not be high. What is that? You may see figure of merit. Name is having merit, so it should be high. No, it should also be as low as possible. Let's read. It is the product of TPD and PD. It is the product of propagation delay and power dissipation. It should be as minimum as possible. It is expressed in picojoules because it is nano, it is a milli. Nano into milli will give you pico. What is that? The time seconds into watts joules. It's like a energy consumption. You can say power should be as low, speed should be as fast. That is TPD should be low. If both of them should be low, your figure of merit should also be low. Okay, because so you can say here FOM is equal to TPD into PD. This one should be as minimum as possible. Right, energy, that's why joules. So it should be as minimum as possible. Right. So the next one. What is the general meaning means, Bhargavi? Figure of merit is the specification of the logic family which indicates the what we call the power dissipation and propagation delay product. Okay, it will one way it will specify the merit, but it should be low. When it is low, it is good. One way is you can understand if you have one particular gate, that gate on an average how much energy it will dissipate. But that is also not correct here. Actually, it is not. This is the delay. Okay, this is the power dissipation. You cannot relate them because power energy generally depends on how much time you operate it. Okay, so but it is also one way to express your figure. Why? Because we need both of them low, because I told you there is a trade-off between TPD and PD. One increases, one decreases. Finally, what is FOM you are having? If you have least FOM, you can say you should prefer that. Okay, so let's move to the next one. So the next heading is figure of merit. Figure of merit, it is the product of, what is that? Why figure of merit came here? Just wait. Figure of merit is already discussed, right? So 1 minute, 1 minute. I will give you. I want to give something else, but something else came. What happened to my fan out? Yeah, yeah. Read this. Fan out. It is the maximum number of gate inputs that can be connected at the output of another gate. That is, you have one gate. At this output, how many other gate inputs can be connected? This is what we call fan out. Fan out is the maximum number of gate inputs that can be connected at the output of another gate. It should be as maximum as possible. So if you are able to connect more number of gates, it is more advantageous for us, definitely. So mathematically, it depends on two factors. What are they, sir? Current sourcing and current sinking. TPD depends on switching, and not only switching, you can say it is depends on your load and load capacitance, resistance of the circuit. Okay, and also switching delay of your transistor. All the things. So now come here. Fan out is the maximum number of gates that we can. You understand what is the meaning of fan out? Everybody, tell me. Then I'll explain what is current sourcing and current sinking. Okay, right. Now listen here. So let's take one example of this inverter. Say for this inverter, I have connected another inverter. This is my circuit, for example. Assume this is my circuit. So suppose if output is equal to 1. Okay, in this circuit, if output is equal to 1, say for example, input is 0, A equal to 0, then your transistor will be in off, ideally open circuit. It may have some voltage, whatever maybe, you assume it as an open circuit. And this is the circuit, right? You are having. Will you accept it? When input is 0, the transistor here will be in off condition. It will act like a open circuit. You just remove this part. Now this will drive this inverter. This is what we call current sourcing. It will act like a source to the external gates connected. How much it can give? It cannot give any amount of current. It is having a limitation. Maximum it can give how much current? VCC by RC. So each gate is requiring some current. Like that, I connect 1,000 gates, sir. Not possible. It can give only this much current. So it depends on how much each gate is required. You can decide that how many gates you can connect. I'll come to that point. Okay. So now, similarly, let's take one more example. If output equal to 0, that is your A is 1. When A is 1, the transistor will act like a on, almost like a short circuit. The transistor is in on condition now. Okay. So now what happens? It is like a short circuit now. So what happens now is it will collect all the currents from this source and this also. It will like a sink for the incoming currents. Okay. So this is the current you will be getting. Okay, how much current it will sink? This much current and this much. Every current will be sink through ground. Here there is a limitation. Your IC should be less than beta IB for saturation. Right, very good. In the saturation, it will provide a voltage of 0.2, and it's I hope you know it, 0.2 volts you get, and it is not exact short circuit, almost like a short circuit. Okay, so it will provide a current IC should be less than beta IB. So here it cannot sink also as much current as possible. It can take this current VCC by RC and some extra current. The total current should not exceed beta IB. So here it can give some current. What is the maximum current he can give in this circuit is VCC by RC. After that it cannot give. So based on these two, I can say how many gate outputs I can connect at the how many gate inputs I can connect at the output of a particular gate. That is what we call fan out. Okay. So fan out depends on two things: current sourcing. When the logic gate output is at logic 1, the transistor is in output transistor is in off condition, and the gate acts like a current source to the external gates connected. And when the logic gate output is at logic 0, the output transistor is in on condition. And what is that? Gate acts like a sink to the incoming currents from the external gate. Okay, based on these two, we decide how many gates you can connect. How to decide, I will tell you. First, up to this, clear or not, please tell me. Very good. Very good. So now let's see how to calculate that. We have taken one example of the gate, that's all, not inverter. One input. It can be any gate. It is just for example. It can be any gate to any gate. It can be NAND, or for easy understanding, we have taken this example. That's all. Okay. So now, see, this gate can be anything. This gate can be anything. Why this is called NOT gate, you are asking? Why this is called NOT gate? What is your doubt? Please ask Abhinay. I told in place of NOT, you take NAND gate also, OR gate also. Okay, it can be any gate input. Just it's a input of some gate. It can be anything. It doesn't matter. There is no rule you should connect NOT to NOT. It can be any gate. Just for general example, we took. Okay. Now let's take one example. Say I am having one gate. Okay. It may have n number of inputs. Don't worry about it. That is not our concentration here. For this output, we are connecting n number of inputs. of other gates. They can be any gates. Okay, like this you have connected n number of inputs of other gates. You may join two inputs, then you should consider it as two inputs. Okay, I have taken this example. So when the output is equal to high, when the output is high, now I am the source. I am giving some current of IOH. Each requires a current of IIH. So at this case, what is the number of gates you can connect? For simple example, this fellow requires minimum 1 milliampere to work properly. When it is in high, it requires 1 milliampere at the input. Here also, this fellow requires, for the input to be treated as high, this fellow requires 1 milliampere. This input requires minimum 1 milliampere. This fellow can give only 10 milliampere. Now in this case, if you connect 5 gates, each gate will take 2 milliampere, no problem. I can connect maximum how many number of gates here? 10. If I go beyond that, if I take 11 gates, the current will be divided as 10 by 11, which will be less than 1 milliampere, then the circuit will suffer. That's why this will decide how many gates you can connect. So it cannot give any current. There is a limitation in the internal circuit. It can give maximum VCC by RC only. Okay, so that's why how to calculate fan out in this case. In this case, how to calculate fan out is we give the name F fan out high. Okay, so it is given by FOH. It is equal to current IOH by IIH. It is the specification will be given by examiner only. Examiner will tell you IOH of the gate is this much. That is high may it will give this much current. What is IAH? In when the input is high, it requires this much current. Input current required for high. Yeah, generally same type of logic families we connect it for calculation purpose. You can see some cases it is compatible. Then we should see the specification. Some every time it is not 0 volts and 5 volts. Sometimes 3 to 18. Sometimes negative voltages will be used. So it should be sometimes you can connect one logic family to another logic family also. In that case, we should check the compatibility according to the voltages available. So IOH is output current in high. Okay, this will give you FOH. Now, similarly, similar to FOH, we should also have FOL. What is that? Fan out when the output is low. Let's take the same example. Okay. Now, when your output is low, okay. So now, yes, correct. When output is low, now it is working like a sink. In this case, how much this fellow is taking, how much each gate is giving. Okay, so what is your FOL is IOL by IAL. Here also limitation is there, na, it cannot go, IC cannot be less than, IC should be less than beta IB. All sinking current should not reach beta IB. It should be less than beta IB. We should manage the number of gates such that its current should be less than beta IB. Now, what is fan out? I will conduct one poll. What is who opted D here? D got 7%. D also there. Okay, done. Listen here carefully. I will tell you the example. So FOH is 10, FOL is 8. I ask you how many gates for this particular gate output. I ask my question is how many gates I can connect, sir? Sir, when output is 1, you can connect 10. When output is low, I can connect 8. That I say. No, sir. Generally, please tell me every time I cannot change the number of gates. I cannot change the number of gates. So I want a number which satisfies both the conditions. I want a number which satisfies both the conditions. What is that number which is happy for both the cases? 8, right? So accordingly, so what is that for any input? For 8 is okay for both of them. 10 is not okay for both of them. 10 will be okay for 1, not for 0, because you don't know when the output will be 0, when the output will be 1 every time. So every time you cannot change the number of inputs, sorry, number of gates connected. Once you have connected, output can be anything. So in the circuit, so what we do, we take both of them. You should take minimum. Then you may go back. People will get this kind of doubt, sir. Here in the definition, you said maximum. Okay, but here you are saying minimum. Sir, is it correct? Yes, it is correct only. Please understand. Your your circuit will be good when minimum of this is your taken as a fan out. That minimum should be as high as possible. That is the meaning. That is 10 and 8 is there, 180 is there, 2000 not possible, just I am taking the example, 1900 is there. Which one is the best case of all the three? Okay, so that's what I said. That is the meaning of maximum here. It is not take the maximum of these two. It should be as maximum as possible. You should design such that your both the cases, okay, you should get as high as possible. The equation which satisfies both of them should be as high as possible. Any doubt, please ask. Otherwise, I will move forward. As high as possible. Now, another thing. For example, for TTL, logic family, you take IOH, Need not be. So here sourcing, you don't know now how much this fellow requires. Here it is VCC by RC, okay. But here you don't know how much this fellow requires. There is no relation with this beta IB and this case. IOH. For example, I am taking, don't write TTF, 400 microamperes, 40 microamperes, 16 milliamperes, 1.6 milliamperes. Suppose this kind of example is there. What is FOH here? 400 by 40, 10. What will be FOL here? 16 by 1.6, 10 only. And what is fan out? It is a minimum of 10 comma 10, which will give you 10. This is 10. Okay, this is how you calculate when these values are given. Shall I move further? The next specification? Yes. Now the next one is noise margin. Wait 1 minute. So the next one is noise margin. What is noise margin? It is the maximum amount of noise that can be added at the input of a logic gate which cannot affect the output of the output logic. It should be as maximum as possible. Simple, I will explain you one thing, then I will give you practically the meaning also. Suppose you have a gate. It is at 0, this is at 1. What is the output? 1 only. So here some noise is added like this. Okay, so here this noise amplitude, okay, is this much. Still it is rated as 0 only, and you will get, it will be read as 0 only, and you will get 0 only now. Okay, so if it is increased this much, still read as 0 only, you get 0. If it is increased further this much, okay, then it may read as 1, and I may get 1, and every time this toggling occurs 1010, this kind of disturbance can occur in the output. So like that, this fellow can bear up to how much? This is what we call noise margin. You give this much, I am happy, okay, okay, I am okay. Even you give this much also, I am okay. My system will not be disturbed. My system will not be disturbed even for this much also. This kind of what we call noise margin. I am not saying noise should be as high as possible. I am saying noise margin should be as high as possible. You understand here? It is the maximum amount of noise that can be added. I am not saying add maximum number of noise. That can be taken by this fellow, okay, at the input of the logic gate, which cannot affect the output. Is it clear how we calculate? I will tell you. Firstly, if the definition is clear or not, please tell. Okay. So now let me explain you with the help, with the help of figure, how to calculate the noise margin of a logic family. Okay. So now listen here. When output is at 0, this is your output logic. Output is at 0. Okay, output is at 0. What is the meaning of 0? It should be 0 volts ideally. But it is not 0. By chance, it can increase up to this much. Because the transistor is in saturation, you expect it as 0, maybe 0.2 volts will be there already. So let me explain better with one example first. See, for example, there is a diode here. Okay, here you have the output transistor which is giving 0.2 for logic 0. Diode requires 0.6 volts to turn on. So in this case, what is the condition I can say? For 0 it should off now. How much noise I can add here? Still it will be at 0 only. You can add 0.2 here, no problem. 0.3 here, no problem. 0.4, then problem starts. So maximum you can add up to 0.4. Yes or no? You can add at this input maximum. Already it is at 0.2. You require 0.6, then the condition will be changed. So maximum you can add 0.4. Same logic here. That is what we call noise match. That is how you calculate also. So here, for example, when output is low, already it is ideally it should be 0 because of some circuit conditions. This is at up to this level. It can be any voltage. Okay, but when I read input, I will read up to this also. I will read up to this also as 0 only. That is 0 to 0.6 is my 0 only, but my output is already at 0.2. This difference, whatever you are having, is called noise margin low. Okay, when the output is at low, you can have this much noise. Make this much noise. I am okay. I am happy. I don't have any effect. Understand? This is what we call noise margin low. What is noise margin low, sir? It is the voltage difference between VIL and VOL. Similarly, when your output is high, ideally, for example, you assume for easy understanding, it should be 5 volts. But due to some resistance drops, everything, it has decreased this much. Minimum, it cannot decrease this much, for example, for your system. Okay, your output is high, it is 5. Because of some drops, it has decreased this much. We will assure that your output coming from the system will not go beyond this. That is the minimum meaning of minimum. It will not decrease beyond this. That is the assurance you have given from your output. Now for input, I don't need this much, sir. I need up to this also. Okay, I will treat it as high only. If it is going below this, my system may not work properly. I may not treat it as high. But here up to this, it is okay for me. Okay, so this is what we call VIH minimum. Here you are, whatever you are having, this is what we call noise margin when the output is high or input is high. At the input, What is the noise margin? Is this minus this. That is, please see here. You can add a negative going, a positive may no problem. Negative going like this, maximum this much amount, no problem. Your input can bear up to this. If it is beyond this, if input is dragged, this line is gone up to this, then problem occurs. This system, this is how you read input. It will not read it as 1. It decreases from here to here also, still it reads as 1 only. This is what we call noise margin. Hi, ask me anything. What is total noise margin? Again, same story I will tell you. Okay, firstly tell me this one. Thank you, Chaitanya. One example of output. See here, actually, I can draw the circuit. I'm sorry, it is collector. Okay, this kind of circuit is there. I'm not drawing the complete circuit. Okay, so this is the point P. At this point, okay, what is the voltage required is this base emitter junction, this base emitter junction, this base emitter junction. Total, you should require minimum 1.8 volts. Okay, minimum 1.6 or 0.7, whatever you take. Say 2.1 you take. Okay, 1.8 you take. After drop, it will become 0.7. So minimum 1.8 is required here to treat it as high. So when the input is coming, it should drive my circuit such that this voltage drop should be more than 1.8. If I go, if because of some noise or something, if it goes below this, okay, then it may be 0 or may not be 0. Okay, but it will disturb your system. It will disturb the system. Okay, so this is what we call noise margin. Okay, so not 0, no, there can be some range where it is not 0, not 1 also. It is purely depends on specification. So I say 0 to 0.2 volts, it is 0. I say 5 to 2.4 something, I said it as 1. What about middle one? Middle one is the unused range. Okay, so system may fall into that also. That should also be avoided. Okay, so everybody clear here. One important relation in exam point of view is where can I write? Okay, I'll write here. Okay, so VOH is always greater than VH, greater than VL, greater than VOL. This is the important relation. Earlier they have given in ES also. It is obvious also. So similar to fan out, what is noise margin? If I ask you, what is the formula for noise margin? So that it can increase. Here it will tell you it can decrease, negative going. Here it will tell you increase. So both the cases to be satisfied. What is the voltage you can add peak to peak? You can say, I mean positive and negative way. Or when it is in output is in low and output is in high, every time whether you when your input is in low or high, anytime system should be safe. So that what is the noise margin I can add? Can I say minimum of, yes, correct, NMH and NML. a condition which satisfies both of them. For example, VOH is some 3.2, VOL is 2.8. Okay, right. VIL is 0.6, VOL is 0.3. What is the noise margin high here? Minimum of 3.2 and 2.8. Sorry. High minimum. It is difference of 3.2 and 2.8. Here it is difference of. So what is the noise margin? So that any case it is say 0.4 and 0.3 ka minimum, which is 0.3. Which is 0.3. I did wrong. 1 minute. Yeah, this is VAH only. High na? Done. So this is a generalized example we can use. So let's move to the last point. Last point. So one more important concept to understand this logic families is wired logic. It's not wild, wired. Okay. When two gate outputs are connected with a wire, the junction will act as a wired gate. That is what we call wired logic. Except in ECL, generally in all other logic families, we call it as a wired AND. In ECL, it is a wired OR. Okay, we are not going through it. Why? Because this is not part of our condition now. But in CMOS, we avoid wire. This I will tell you. When we discuss CMOS, I will prove it. Okay. During CMOS, I will explain. Now, let me give you the explanation with the help of one figure. Suppose you have two gates. So, both the gate outputs are connected with a wire. This junction will act like a AND gate. It is not gate, but this wire will act as an AND gate. I will prove it. I will prove it also. You take A, B, C, D. What is the answer here? A, B bar. Here, C, D bar. What is the answer? A, B bar plus C. A, B bar plus C, D bar. Okay. A, B bar plus, sorry, why plus? A, B bar dot C, D bar. For wired AND gate, because this junction will act like a wired And so if it is a wired OR, depending on the logic family, we take it as a OR operation. Generally, examiner will tell you in the problem whether it is wired AND or OR. We'll do the problem also based on this. But before that, let me go to explanation. Let me prove. You may not be satisfied if I say this as a AND gate. You should understand. You should ask me why, or you may have the doubt. Prove it. Let me prove it. Okay. So what is why? Okay, Chaitanya. So this is A bar, right? Now let us take one more gate. This is V bar. Okay, up to this clear now, everybody? Now I take a wire, connect them. What is this output? This will be equal to, I want to prove A bar into B bar. Okay, let me prove it. Let me prove it. Suppose you have a switch S1, another switch is there S2. Can I say any one of them short circuit? If both are short circuit, short circuit. If first one short circuit, parallel, zero parallel with anything is zero. So any one of them short circuit, overall is what? Overall short circuit. So you can say here, if any one of them is zero, overall is what? Zero. Okay. Short circuit is like zero, you assume. Okay. If any one of them is short circuit, overall is short circuit. Any one of them is zero, overall zero. What is this operation? अरे शॉर्ट सर्क्यूट में क्या वायलेशन क्यों होता है? Zero shorts parallel with zero is possible. It is not source. What is this operation? Two shorts can be parallel, two sources cannot be parallel. And what is this? AND operation. Okay, so same logic is applicable here also. You see, if this input is 1, this will act like a short. If this input is 1, this will act like a short. So any one of them input is 1, that particular will act like a short and output is 0. So any one of them is any one input equal to 1, output equal to 0. Which operation it is? NOR operation, which is A plus B whole bar, nothing but A bar into B. Is it clear? When both of them are ones, then both of them are off, then only you will get one. Sorry, when both of them zeros, both will be off, then only you get one in the output. So it is proved here or not? Two gate outputs connected with a wire will act like a AND operation of both the outputs. This is what we call wired logic. This condition is avoided in CMOS. This condition is avoided in CMOS, and there is another case called totem pole configuration that is not in our syllabus now. We are not discussing, but why it is avoided in CMOS, I will discuss it. When we discuss the CMOS logic family next, I will discuss that why it is not allowed in CMOS. Okay, this is not allowed in CMOS. Reason we will discuss it. Now, before that, let's do one question. One small question. Where are we? Yeah. Read the question. Story is ready. Too early. Abhinay, Kritik, Asif, all 1/2s only. No 2/2. Okay. Let's see what is the right answer here. It is a simple one step. You will get the solution. Logic gates shown in the digital circuit below using strong at output. When the pull down are off, okay, the high value resistors are connected to the output logic levels to high. That is pull ups are weak. Okay, pull down is strong, pull up is weak. Okay, it doesn't have any effect in your solution. Note some nodes are intentionally shorted to implement wired logic. This is a wired AND gate. And this is also a wired AND gate. Okay, such shorted nodes will be high only if outputs of all gates are high. That is meaning is wired AND only na. When all are high, then only high. What is this? What is the meaning of this AND gate? That's why I took AND gate. Then he only told that it is a wired AND gate. He will tell you that. The number of distinct values of x3, x2, x1, x0 out of the 16 possible values such that y equal to 1. How many minterms your output is 1? That is the simple line. He asked it little critically. Okay. So now let's do it. What is this value, man? x0 bar. What is this? x0. Forget about this value. Take it as some name k. Yeah, I'm not doing this XOR operation and all those things. What is the value? You will get it here. It is the multiplication of x naught. Okay, 1 minute. X naught bar into x naught into k, which is 0. Okay, this is by default 0. Here, what you have? X3. What is your y? X. So, if x3 equal to 1, output equal to 1. So that is 1 followed by all cases. 1 triple 0 to all ones. That is 8 possibilities. Yes, 8 to 15. Total how many combinations it will give? 8. Examiner has given the first lines to say that your output y is, say here, pull down, strong pull down. When it is 0, it is connected to proper ground. Okay. When it is 1, it is connected to the supply with some high resistance, which will take some drop. So ones may not be that much strong. Strong in the sense equal to your required value. Okay, we can say it is a weak one. That case, it is a strong one. We discuss a strong one, weak one conditions later. I mean, now in this class only mostly. But that is the meaning of it, which is not affecting in your solution anyway. Solution is not affected by this. Solution is purely wired logic if you know sufficient. That also you need not know. Examiner only told that. He only gave it whether it is wired AND or OR. So any doubt in this, ask me. Otherwise, we'll move to the next. Okay. Fine. The next one we are going to discuss is MOS. Now we are coming to MOS. Why MOS? Because examiner want. Okay. Yes, MOS. Okay, MOS is MOS. So what is the symbol for PMOS and NMOS? You study PMOS, NMOS, everything in your EDC and analog very well. We are not discussing that much here, but whatever required for you, I will give you that part as my responsibility. So this is the symbol for PMOS. Source, drain, and gate. This arrow indicates source to drain positive current, P channel MOSFET. You can also represent this figure like this. It is called enhancement and this is called depletion. Okay, that is not our job to discuss this now. You can also represent PMOS like this. Why this bubble comes, I will explain. Just wait for some time. Similarly, NMOS. Okay, so here arrow direction will be reversed. You need not have bubble here. Right. So these are the symbols of PMOS and NMOS. Okay, this arrow indicates source to drain. This is depletion and enhancement mode. Now, what I want to give you is to start the conduction in the MOSFET. Like for a diode, to turn on this diode, you need to give some voltage called as cut-in voltage. Similarly, for MOS, okay, for MOS to start the conduction, to form the channel of conduction between your source and drain, okay, we should provide some voltage, which the minimum voltage you need to provide is called as threshold voltage. Threshold voltage is to be provided between gate to source. Okay, so listen here. I will give you a few points now. First point, threshold voltage is the minimum voltage required for conduction. Threshold voltage is the minimum voltage required for conduction. Threshold voltage of PMOS is negative. Threshold, so PMOS is on if VGS is more negative. That is magnitude wise it should be more, but PMOS is on when VGS is more negative than threshold voltage. Next, NMOS, I'm sorry, wait. Threshold voltage of NMOS is positive. NMOS is on if VGS is more positive. Okay, then threshold voltage we call VT. Then VT. Okay, so VGS is more positive. In any case, you can say your VGS must have a magnitude greater than VT. This is the condition for turn on your PMOS or NMOS. And another condition you can say is When VGS is equal to 0, both PMOS and NMOS, I'm sorry, equal to 0. Sorry, equal to off. Right. Very good, Aditya. So when it is more negative, then PMOS will be on. When it is more positive, then NMOS will be on. Why this bubble is shown? One way you can say negative. Another way is we discuss it now. That is for 0 it will be on. For 1 it will be off. Like that logic also we can take. Now let's understand here few more important points. PMOS is strong in passing 1, weak in passing 0. Okay. Similarly, NMOS is strong in passing 0, weak in passing 1. So PMOS is strong in 1, NMOS is strong in 0. PMOS is weak in 0, NMOS is weak in 1. What is this weak and strong one? What is the meaning of it? Let's have the understanding. Let me prove those conditions, or let me explain the meaning of those conditions. So let me take, say I have one NMOS. Just 1 minute, can you give me time? I need to switch off this. Just 1 minute. Oh, really? I'm not intentional. I'm intentional in 3 colors, but wow, we got these 3. Very nice. Okay, so now from here to here, to pass the data from here to here, 0. This is what we call pass transistor. If you want to pass, why to have transistor, sir? You can have a wire also. Wire will also give 1, you will get 1, 0, you will give 0, it will get. Okay. So why to have a transistor to pass the data, sir? Listen. See here. Here your gate voltage is there. Okay. So when gate voltage is 1, suppose when VGS is 1, then it will be on. Then only it will transfer. If it is 0, this fellow will act like off. That is, even your data is there, it will not come to the output. So it is transferring the data with control. That's why it is called pass transistor. It can pass the data provided your gate is biased properly. Gate is having the control here. When gate is 1, it will pass. When gate is 0, it will not pass. You understand the logic? Okay. Now, let me prove that it is strong in 0, weak in 1, whatever those conditions, let me prove it. For that, I need to have one load. Let us assume it is a capacitor. Okay. So here you are having the input Vg, or you make this Vg equal to, this is the gate terminal, source and drain. You make it equal to your Vg equal to VDD. Okay. So suppose this is what VGS. What is VGS? What is VGS? It is Vg minus Vs. It should be greater than Vt. Okay. This is the required condition for the transistor to on. Everybody up to this clear or not? Okay. Now, because I have applied this VDD, assume there is no voltage initially. If it is initially 0, assume this Vc equal to 0. Initially, it is 0. Vc equal to 0 initially. So VDD minus 0 is VDD. Assume it is greater than threshold. So the transistor will be on. Now here I apply my input is equal to 1. What is the meaning of 1? Assume VDD. I applied 1. Now what happens? So this 1 should transfer here. That is our aim. Okay. So now what happens after giving this one to some resistance in this path? The capacitor starts charging. Slightly it becomes networks class, or almost like networks class. Okay. Now the capacitor starts charging. Your capacitor, what is that? The voltage across the capacitor starts increasing. So the input is 1, it starts charging. Input is 1, it starts charging. The voltage across the capacitor starts increasing. It increases, but there is a limitation. Your gate voltage is VDD. Okay. What is this? Minus. What is Vs? What is Vs? Voltage between this and ground. What is that? Tell me here. What happened here? Yes. Vc should be greater than Vt. Now we will come with one limitation. VDD minus Vt should be less than, greater than, this you take this side, this you take this side. So your output Vc is less than VDD minus Vt always. This is what we call weak one. You gave VDD, but this fellow is not able to develop VDD. What happens, sir, if I, because it is there, it will charge, sir. What is there? It will charge. Once it charges beyond, if your capacitor charges beyond this value, if capacitor charges beyond this value, immediately this fellow will off. Because VGS should be greater than VT. VGS should be greater than VT. So it cannot charge beyond VDD minus VT capacitor. So the output is always, even you give 1, you don't get 1 exactly. VT is the threshold voltage, man. It is a fixed quantity depending on the MOS specification. Okay. So for example, this is 5. If you want, for example, VDD equal to 5, VT equal to 1. So VC is must be less than 4. It cannot increase beyond 4. If it becomes beyond 4, that is, if it is 4.5, 4.1 it want to become. It is 5. 5 minus 4.1 is 0.9. So stop. So even you give 5, you don't get 5 in the output. That's why we can say NMOS is weak in passing 0. Okay. So now up to this clear or not? Ritik, I will explain that. Yes. Up to this, is it clear, my dear friends? Yeah, capacitor is the load. We took capacitor as an example for your load. Okay, now let's do what happens if it is 0. If your input is 0, what happens? Input is 0. Yeah, load can be anything. We treat it as a load capacitance for the time required for charging. Load can be anything, but output should reach the load or not. You connect anything, this should come here. Whatever it comes, this voltage cannot be beyond this. Whatever you do, Vs cannot be more than, you can say it is Vs should be less than VDD minus VT. That Vs cannot get VD. How it can reach easily? Show me, Hussein. You keep resistor. Okay. Assume no capacitance. Okay. Can you keep here 5 volts and here also 5 volts? I gave here 5. It will not on, na? It will not transfer it. Here we are taking, in fact, device capacitance also into consideration. So now, listen, the next one. Yes, mass input is a capacitance. So output may be another mass. It may be another gate, na? So plus VD. Okay, this is your VG. And now the input is made equal to 0. 0 means what? Ground. Okay, here also let me take the same example. Okay, you assume capacitor is having some charge initially. Okay, so in this case, whenever you provide the ground, what happens? The transistor is in on condition and the capacitor will discharge. So discharges VD D minus Vc should be greater than Vt. If Vc becomes 0 also, no problem. Still VDD minus 0 is greater than Vt. Happy. Still it will be on. I mean, if even it is having some initial voltage, not having also, whatever may be, it is fully discharged also. Still, you will get it is in on. That is, it can transfer 0. If it is already having 1 also, it will discharge. Okay. If it is some having already 0, no problem. It will stay at 0 only because this 0 is connected to here. So it can make, you can make this node voltage 0, no problem, because even it is 0, gate minus source is more positive than threshold. So still it will be in on condition. So it is strong 0. Strong 0 means whatever you want, you are getting that. For 0, you get some voltage. Suppose this capacitor is not able to discharge completely, it stop at Vt, then it is not strong. Yeah, current can flow from any direction to here. Charge is. You understand one more thing, Sahu, Aditya. Source and drain are interchangeable. Okay, you have provided here. See, here you provided the voltage. Here you provided the short. If steady state, may both are short only. No current will flow at all. So is it clear? So for storing data in place of this DRAM, we discussed that later in maybe in day after tomorrow class. Okay, that is a different case. It is similar to that case that we discussed in the DRAM. Okay, Hrithik, dynamic RAM condition. Yeah, anywhere you can interchange source and drain, no problem. Aditya. So is it clear? It is proved that NMOS can transfer 1 weak and 0 strong. Now, you can prove similarly. We can prove for PMOS, it is strong in 1, weak in 0. Just reverse conditions, you can prove it happily. Is it okay? Shall I move further? Okay, fine. So now NMOS, sorry, first we discuss PMOS. PMOS logic family. Tomorrow, 1 minute. Tomorrow doubt session also. Every EC student please listen. I may discuss theory at least 1 hour. Don't miss it because day after tomorrow we finish this EC part and we start after that microprocessor. So tomorrow please adjust. Half I may take doubts, half I may take theory also. So don't miss because it is a doubt session. Because EC people are less only. I'm announcing in the class itself. So please come tomorrow. Don't miss it. Okay. So PMOS logic family. So here also triple E also there. Thank you. How many are EC then? 3, 4 only. Ritik is EC. Only one. Okay, okay. Not one, yeah. Whole. Okay, take it. We are calculating EC first. Then very less people. So hardly only 3 students from EC. You made a people. You are also triple E. Okay. Then very less. You want again pull. What happened here? No problem. Leave it. Okay. Okay. For you, I am doing again. Wow. Okay. Fine. Now poll is not updated. Leave it. Poll is little angry on us. Okay, let's continue. Let's continue. So let me take logic 1 equal to 0 volts. Logic 0 equal to minus VDD. Is it positive logic or negative logic? Is it positive or negative logic? It's a positive logic. 0 is more negative, 1 is more positive. Voltage can be anything, okay, doesn't matter. So it is a positive logic only. Now, first PMOS, let's take one circuit. So this is your transistor Q1. Okay. So now A transistor Q1 and output Y. So this is what we call active pull-up resistor. It is just like a resistor only. Permanently conduction, this will act like a resistor, so that it requires less area compared to conventional resistor. So in the circuit design, we take this active pull-up resistor. Okay, now when A is 0, when when 0 means how much here? Minus VDD. When A is 1, 1 means how much here? 0 volts. So when A is 0, what happens? It is minus VDD. Minus VDD is minus. What is the gate to source voltage? Tell me. What is gate to source voltage? Minus VDD. So gate to source voltage is minus VDD. Gate to source voltage is more negative, then the transistor will be on. Similarly, when it is 1, what is 1 here? 0 volts. If it is 0 and 0, 0 minus 0 is 0, transistor will be in off. So first case it is on. When it is on, short circuit. Short circuit mein how much voltage you get? 0 volts. But 0 volts means 1. Second case it is off. Off means open circuited. You get this minus VDD after some drop. Some minus VDD will come here. That is minus VDD is equal to 0. It's not buffer. You give 0, you got 1. You give 1, you got 0. So it is nothing but PMOS inverter. Because see, for 0 it is on, for 1 it is off. You can represent with this symbol also. Inversion. For 0 it will be on, 1 it will be off. Is it okay? It's nothing but a resistor, simply like this. Okay, some minus VDD. You take one resistor. Okay, this resistor on distance is this resistance is given by the on distance of this device. We call it as active pull-up. Instead of passive resistance, you have taken active resistance here. Active element as a resistor. The resistance offered by this is your pull-up resistance. In silicon, space may be reduced because of this. Now come back. So let's implement NAND gate or NOR gate, whatever maybe. Let's try. These are the biasing voltages. Now let's take series combination first. Just now I told na, for if in the IC manufacturing, okay, IC manufacturing, resistor may take more area compared to your semiconductor device. Now, okay, so now listen here. Let me take the transistor Q1, Q2. So you are having A, B, Q1, Q2, and what is the output? Zero 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 one 10 11. Okay, if it is 0, I'd already told na 0 is on, 1 is off. If both are, any one of them is open circuit in the series, if you have some open circuit, overall is open circuit only, then you get minus VDD. Minus VDD means 0. When both are on, both will be short circuited. I will get 0 volts. 0 volts means 1. Okay, so now you can prove it as an OR gate. So for series, it is NOR gate. Similarly, you can prove. Good evening, Jitendra. In fact, good night also, as the class is going to end. Okay, so let's take this. Wow, you are from mechanical. Then why you came? Thank you. Very nice. Today, other than EC, more number of mechanical triple E people are there in my class. What is the reason? Oh, just wandering all the live classes. Fine, fine. So now A, B, 0 0 0 1 1 0 1 1. So here Q1, Q2. So if it is 0, as usual, same story. 0 may what is the condition? On. 1 it is off. Okay. Now what is the output? What is the output? When both are, any one of them on short parallel, any one of them is shorted, overall is short only. Any one of them is on, you get 0 volts. Otherwise, you get minus VDD. So 0 volts is 1, minus VDD is 0 for us. 111, 0. This is nothing but NAND, because it is a parallel. For parallel, it is NAND gate. Okay, let me do small thing here. Yes, because I think time up, he will come to notify. If you wait some time, he will shout also. 2 minutes, I will leave you. Just I want to do a little difference. Now, by negative logic, what happens that I want to give you. Then we can end the class. It's not zero, Ritik. Some microamperes it will go. That's why earlier also you see here, I took the example. There also I took in microamperes only. These are the ideal values. We treat it as an open circuit. So where we are? PMOS logic family. This part is discussed, and now see here. I want to do small difference to the analysis we have done. I take reverse, for example. So logic 1 is minus VDD, logic 0 is 0 volts. Then this positive logic will become what? Negative logic. Now listen here. Same circuit, but here the difference is 1 minute. If you give here 0 is 0 volts. It will be off. Then you get minus VDD. That is 1. If you give 1 minus VDD, it will be on. A to source is negative. Okay. And now it will be, when it is on, it is 0 volts. Okay. Here, understand, it is inverter only. PMOS, same inverter circuit only. Okay. But here, 1 is on, 0 is off, because it is discussed in negative logic now. Now, in this circuit, there is a difference. It will not be NOR gate now. Let me prove. So if it is here 0 means now how much? 0 volts. When it is 0, it is off. For 1, it will be on. Negative logic we are speaking. Okay. So now please understand, if it is both are off, both will be open circuited, you get minus VDD. Minus VDD means 1. Okay. Both are off. So any one of them is on. Any one of them is on. Then what happens? Here both are on. Short circuit. You get 0 volts. Last case both are on. You get 0. That is 0 volts. Okay, in any one of them is on. If any one of them is on, any one of them is off. This is off or this is off. Series may it is off only. So off you will get minus VDD. That is 1, 1, 1. So now it will work like a NAND gate. For which one? Negative logic. And this, I'm not doing it. You can understand similarly. Okay, this can be written as similarly. It will be NOR gate. in negative logic. Okay, conclusion. In PMOS, okay, for positive logic, series is which operation? NOR. Parallel is NAND. For negative logic, parallel is NOR. Series is NAND. Both are dual to each other. That is the conclusion. Both are dual to each other. Okay, so few more. Let me give you lastly TPD, power dissipation, noise margin, fan out. Okay, this will be 300 nanoseconds, 0.2 milliwatts, approximate typical values. You need not remember them also. Noise margin will be around 1.5. This will be around 50. So these are the typical specifications of which one? PMOS logic family. So that's all for today. We'll meet tomorrow. Tomorrow I will do some questions of previous also. We'll take some kind of quiz like previous weeks. We'll try that. Then we will do some part of this NMOS technology and all also. So we take both of them, mixed class. So that electrical people will also enjoy some part. Okay, people, tomorrow you can ask me in the doubt session. No problem. We'll discuss there. Anything else? So good night. Good night all. Good night. Thank you. Good night. Good night. Right. So anything else? Say one more thing I want to help you is I want to specify is see NAND gate is directly coming. Inversion come for free. NAND gate is not made by end followed by inverter. NAND is directly available. NOR is directly available. So you understand inversion comes free compared to direct. Okay. In fact, AND gate can be done by making one inverter here. So thank you. Good night. Bye bye. We'll meet tomorrow.